This video covers the last three sections in Chapter 2 of Mano and Ciletti, and you do not have to read the chapter as long as you get these concepts that are in the video. You can read it if you want to. So basically, when the and the or gates that we have been talking about are only two of the possible functions that you can get from having a two-input gate. And this shows you all the possible functions that you could have. So on this slide, each of the functions is given a name. For instance, you can see that F1 here, F1 is an AND gate because it has a 1 as an output only if both of your functions are high. So we've been doing the and the other one is the or, and you can see that that is F7 on the chart, which if we come back, F7 is here. And if either one is high, then you get ones as an output. So it names the rest of these. Some of these that you may have heard of are exclusive or, nor, and NAND, if you've done any of this digital logic before. So I want you to know that you do not need to memorize all these names and all these functions because some of them are used more than others. So what you want to concern yourself with are these gates that are shown on this slide. You have the and or, you already have your inverter, which you know about. A buffer just sends the signal through. Then you have the NAND, and in the NAND, the output is inverted. And the NOR, the output of an OR, is inverted. So it's the opposite of what you think. The exclusive OR means either or, but not both. And you can see that in here. And the exclusive NOR would be the opposite of that. So these are the ones that you want to know about. And that takes us through 2.7 and 8. And so the last section doesn't go into this in great detail, but they just wanted to give you a little information about integrated circuits. So an integrated circuit, there's what they call a die of a semiconductor crystal. Usually people might call it a chip, and that chip is inside these I don't know what you want to call them, chips, whatever. So the silicon semiconductor contains all the electronic components that you would need to create the digital gates. And so each one is designed separately, and it has the various gates that you want in that integrated circuit, into that IC. And so usually all of these have a numeric designation on the top of them, and you can tell what the vendors are. And the vendors will provide descriptions either on the web or manuals or whatever to tell you what you need to know about that chip. So there's other pictures out there. You can go look that up. So this is they just want you to know that there's different levels of integration and that they're categories by the level of integration. SSI is small scale, MSI is medium scale, LSI is large scale, and VLSI is very large scale. In the book, it will tell you what type of circuit might be in these different types if you want to go look that up. Then you have your digital logic families, and they're determined by the circuit technology used to produce that chip. And so they're listing what some of the most common are, and they list here on the right, and this is out of the textbook. You have your TTL, ECL, MOS, and CMOS. So the TTL has been around a very long time. That's called transistor logic. The ELC here is saying that they were good for systems requiring high speed. The MOS is good for systems requiring high component density, meaning that you have a small space to get all your circuits into. And the CMOS is preferable for systems requiring low power consumption. This could be digital cameras, any handheld devices, your phones, tablets. So the TTL and ECL are declining in use. And then the CMOS has become at this point the most dominant digital logic family. And so the last thing here is just that we're looking at computer-aided design of VLSL, which is your very large scale circuits, and that usually on these very large um, circuits, you're using an HDL, which is hardware descriptive language. We talked about this, I believe, in chapter 1. And this has been an important development in the design of digital circuits, especially for the very large ones. It resembles a computer programming language versus looking at gates. And the nice thing about this is that your engineers can uh, be designing using more abstract functionality than thinking about what specific hardware they need. So we've been doing all this gate minimization and everything, and this language could do some of that for you. So then the designers can just focus on what they need to happen in the circuit at a higher level than actually getting down to the specific hardware and what they need. And so with these, is a tool to simulate to verify the functionality before anything would be submitted for fabrication to make sure that you don't make a mistake and waste a lot of money. And at this point, the industry is almost totally reliant on these HDL-based tools designing, especially your VLSI circuits. So there are two widely used HDLs out there, and that is Verilog and VHDL, and we will be using Verilog in this class starting in chapter 3.